All right, so here we have section 2.2. We'll look at some perpendicular lines and lines perpendicular to planes, and continue to look at things like converses and conditional statements. So perpendicular lines are going to be two lines that intersect to form a right angle. Remember, a right angle is an angle that's 90 degrees. So if two lines intersect and they make a 90-degree angle or a right angle, then they are perpendicular. A line perpendicular to a plane is going to be a line that intersects the plane in a point and is perpendicular to every line in the plane that it intersects. So here I have an example of two lines, line N and line M, intersecting to form a right angle, which we use this little box there in the angle to show that it's a right angle. And then the shorthand way of saying perpendicular is to have this basically an upside down T between N and M. So N is perpendicular to M. That's how you would read that statement. And then here we have a line that's perpendicular to a plane. The line goes through the plane, intersects at one point, and then we can see that it is perpendicular. It has a little right angle box going in multiple directions all the way around it. So it's perpendicular in all directions to that plane. So shorthand N is perpendicular to plane P, capital P. All right, so decide whether each statement about the diagram is true. Explain your answer using definitions you have learned. All right, so the first one says two lines or points R, S, and T are collinear. So we remember our definitions from last chapter. Collinear means that they are all on the same line. So if I look at the picture, R, S, and T, all three on the same line. So my answer is going to be true. And so, based on the fact that points are collinear, if they are on or if they lie on the same line. Next one, ray SU is perpendicular to line RT. So in order to be perpendicular, we know that they have to intersect at a right angle or at 90 degrees. And if I look at this picture here, this is ray SU with line RT. And if I look at this angle, if it's a right angle, it should go straight up from there, right? And then we put the little boxes there. Since it doesn't go straight up, it's actually more, if I measure that with a protractor, probably closer to 60 degrees than 90 degrees. It's definitely an acute angle. So this one's going to be false. Angle RSU, that angle created by the line and the ray, is very clearly not a right angle. Based on the definition we learned right up here, perpendicular lines, two lines that intersect to form a right angle. All right, so a new kind of statement. We've talked about conditional statements. Now we have something called a biconditional statement, which is a statement that contains the phrase if and only if. So if you don't see this phrase in it, then it cannot be a biconditional statement. And if we're writing a biconditional statement, basically when we make this statement with if and only if in it, it's the same thing, or it's representative of taking the conditional statement and the converse statement and putting them together to make one new statement. So here we want to rewrite the biconditional statement as a conditional statement and its converse. So two lines intersect if and only if, so there's that key phrase that makes it a biconditional. Their intersection is exactly 1 point. So two lines intersect if and only if their intersection is exactly 1 point. So from that statement, we can make a conditional statement. It's basically going to say, of course, we've got to get rid of the if and only if to make it into a conditional, because then it's going to be in if-then form. And so a good representation of the conditional from that would be if two lines intersect, then they intersect in exactly 1 point. Right, so if two lines are intersecting, then they're going to intersect at exactly 1 point. And you may notice we're going to have to change the wording just a little bit, just to make the new statements make sense based off of the other statement that's supposed to represent both statements together. And then the converse of that we would be creating, remember the converse is basically just taking the hypothesis and conclusion, so the end and the beginning, and swapping places. And so we're going to say if two lines share exactly 1 point, then the two lines intersect. Once again, we had to change the wording a little bit from the conditional statement just to have a statement that didn't sound odd or didn't make sense. So now we're considering the following statement: x squared is less than 49 if and only if x is less than 7. So I have a couple questions that go along with that. First off, is this a biconditional statement? And so when we hear the word biconditional statement, we should be looking for one phrase in particular, which is if and only if. And that's the only requirement we have that makes it a biconditional. So if we look at this statement, if and only if is in the middle of the statement. So that's going to be a yes. Yes, it is a biconditional statement. And there is a B portion that says, is the statement true? So if I look at this statement, of course, remember if it's if and only if, it's kind of like saying if x squared is less than 49, then x is less than 7. Or the converse of that, if x is less than 7, then x squared is less than 49. So, in order to determine if it is true or not, we have to come up with a counterexample, or see if we can come up with a counterexample that would not fit there. So if x squared is less than 49, if and only if x is less than 7. So if I use x equals 1, 2, 3, 4, 5, or 6, those are all less than 7, then my x squareds would be in the order of 1, 4, 9, 16, 25, and 36, all of which would be less than 49. Now, when I look at this statement, it just says less than 7, right? So all of these are less than 7, but there are also other numbers that are less than 7. Right? And if I use some of those numbers, let's see if we do x equals -8, which is less than 7, but it's in the negative scale. But if I do x squared, then -8 squared is going to become 64. So in this case, x squared would not be less than 49. So is the statement true? No. Right. Now, it could be true if this last portion was changed, right? If instead of x is less than 7, if we had a statement that said if negative 7 is less than x is less than positive 7, which then would mean that our x value would have to be somewhere between negative 7 and positive 7, and all of those terms squared would be less than 49. Right, so the following statement is true. So they're telling us it's true to begin with, so we don't have to worry about true or false on this. And then it says write the converse and decide whether it is true or false. If the converse is true, combine it with the original to form a biconditional, right? So in order for making a biconditional, since it's supposed to be made up of the conditional and converse, we really want to make sure that both the conditional statement and converse are true. Otherwise, if one of them is false, when we make the new biconditional statement, then it's automatically going to be false because that conditional or converse were false. So we've got if x squared equals 4, then x equals 2 or negative 2, which that statement is true. The converse of that then is going to say that if x equals 2 or negative 2, then x squared is going to equal 4. Which if I do 2 squared, that equals 4. If I do negative 2 squared, that also equals 4. So if x equals 2 or negative 2, then x squared equals 4. It's going to be a true statement. And so since the converse is true, the conditional was true, then we can make that into a biconditional. Which is going to say x squared equals 4 if and only if x equals 2 or negative 2. So we're taking the conditional statement, the converse, put them together to make one biconditional statement, and we have to make sure that if and only if is in the middle for it to be a biconditional. Okay, so then here we have the converse of the angle addition postulate is true. Write the converse and combine it with the postulate to form a true biconditional statement. So, angle addition postulate. First off, probably have to be refreshed on what the angle addition postulate is from the last chapter. This angle addition postulate said if P is in the interior of angle RST, then the measure of angle RSP plus the measure of angle PST equals the measure of angle RST. So that's the angle addition postulate. Wants us to write the converse. So the converse is going to take the then part, move it to the if part, and the if part, move to the then part, or the hypothesis and conclusion are going to switch places. So our converse to the angle addition postulate is going to look like this. If the measure of angle RSP plus the measure of angle PST equals the measure of angle RST, then P is in the interior of angle RST. So here's our conditional. The original postulate is our conditional. The converse here. Put them together to make a true biconditional statement. And our biconditional is going to say P is in the interior of angle RST if and only if, key statement for it to be a biconditional, the measure of angle RSP plus the measure of angle PST equals the measure of angle RST. And so that completes section 2.2.